Hey there, this is Chipmunk Math. I'm Vince, and in this video we're going to get an advanced understanding of the Pythagorean Theorem. In the video lesson, we saw the Pythagorean Theorem, but we didn't see why we should believe it's true. So in math, if we want to show that something always has to be the case, we have to give a proof. We have to give something that shows logically that it always has to be the case. So let's prove it. Let's see a proof for the Pythagorean Theorem, why we can trust this thing. Now, what we're going to see here is just one of many different possible proofs. There's a huge number of different proofs for the Pythagorean Theorem, so we're just going to see my personal favorite way to prove the Pythagorean Theorem, and I hope you like it. All right, so let's start off with just any old right triangle. Say we've got just some right triangle, and we'll call the sides A and B for the legs and the hypotenuse C, just like we're used to. And we've got a right angle, because it's a right triangle. So if we've got this set up, what could we do with this? Well, instead of just having one of the triangle there, we could make more of them. So we have 4 of these right triangles, right? So we've got 4 identical copies of this right triangle that we started off with, but we're not just going to leave them out anywhere. We're going to make a special shape with them. We're going to move them into this square shape. Now, it certainly looks like a square, but how can we be certain that it's a square, right? Well, first, we see that it has right angles in all of its 4 corners because of those right triangles we made that shape with. But even if it has those right angles, we can't be certain it's not a rectangle, right? How do we know for sure it's a square? So to be sure of that, let's bring in all of those side lengths again. We see those side lengths here, and now if we look at that outer shape of the square, we notice that all of the outer sides of that square are A and B, right? It's both of the side legs from that triangle we started with put together, so all of our outer shape square all have side lengths of A plus B, so we've got right angles and we've got matching side lengths all around that outer shape, so we do definitely have an outer square. Now, on the inside, it certainly looks like we have a square as well, right? We've got C, 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 C. We've got those 4 sides. They're all the same. But once again, we've got the same kind of problem. We can't be certain that we have right angles in there. So how can we be sure that we're looking at a square and not, a squished rhombus shape where it's got all the same side length, but it isn't actually a square because it lacks right angles? So to figure that out, let's go back to that triangle that we started with, right? If we consider that triangle, remember how many angles are inside of a triangle? And sorry, by angles, I don't mean the 3 angles. I mean, what's the sum of the 3 angles inside of a triangle? It always sums up to 180 degrees. So if we know that it adds up to 180 degrees, and we've got that right angle that's already 90 degrees, if we subtract that from the 180, what remains is 90 degrees. It's got to be the case that the other 2 angles inside of the right triangle add up to 90 degrees. Now, if we look at where those other angles show up in that big square shape we made, we see that they wind up matching nicely around the corners of that inner square shape, right? They all show up because of the way we placed those triangles in the first place. And so notice, because that outer square has straight lines making it up, we've got both of those angles on a 180 degree line, right? A line makes an angle of 180 degrees, so that inner square shape for all of its corners has to be the remaining 90 degrees to make that 180 degree line, right? We know those 2 angles from the triangle add up to 90 degrees, so what's got to be inside is another 90 degree so that we can add up and make a straight line of 180 degrees like we set it up. So at this point, we have our right angles on the inside, so we do have a square shape on the inside, we have a square shape on the outside. This is a pretty great thing. So what can we do with this? Well, notice there's 2 different ways of looking at this thing. We've either got a big square, or we've got a smaller inner square that's surrounded by triangles. So because we have these 2 different ways of looking at it that still are the same thing, we can consider the area of these 2 different situations, right? We consider what's the area of that big square, and we know that the area of that big square has to match the area of all 4 triangles combined with the area of that inner small square. So another great thing about this is because all 4 triangles are identical, instead of saying the area of all the triangles, we can just say 4 times the area of one triangle because it's just 4 copies of the same triangle showing up. So what is those values going to be precisely? Well, the area of the big square, remember its side length was A plus B because it had both of the legs from the right triangle making up its sides. So we've got A plus B squared for the area of the big square. And then the area of the triangle, well, area of a triangle is 1/2 base times height, so we've got 1/2 A times B. There are 4 copies of it, 4 times 1/2 AB. And then finally, what's the area of the small square? Well, it's got C for all of its side lengths, so we've got C squared there. So at this point, the great thing about this is we've got this nice equation that we can really get into working on, right? We can do some algebra with this equation. Maybe we can get something to come out of it, some nice like expression will come out of it. And so we start working with this. We've got a plus b squared equals 4 times 1/2 times a times b plus c squared. So a plus b squared, well, we can just write that as a plus b times a plus b. We simplify on the right side, 4 times 1/2 ab. Well, 4 times 1/2, that becomes 2, so we've got 2ab plus c squared. What's a plus b times a plus b, right? We're sort of foiling that out. If you're used to the word foil, we're just expanding those two chunks, those two quantities. A plus b times a plus b, that's a times a squared, a times b, ab, b times a, ba, b times b, b squared. On the right side, we've still got 2ab plus c squared. Hey, on that left side, ab and ba, those are really just the same thing, right? Because we're just changing the order of multiplication, but that doesn't mean anything with these numbers. So a squared plus 2ab, right? We combine those together into 1, plus b squared equals 2ab plus c squared. Hey, would you look at that? We've got 2ab showing up on both sides. So we can use algebra at this point. We can subtract 2ab from both sides, and what remains is a squared plus b squared equals c squared. What do you know? A squared plus b squared equals c squared. It's our old friend, the Pythagorean theorem, right? That's the equation that we were trying to get in the first place. And now the great thing about this is this logic works for any right triangle. When we set this up, we purposely chose a right triangle that wasn't special in any way. We chose a right triangle where we didn't really know anything about it. We just said, yeah, let's call the sides, A and B for the legs, and we'll call the hypotenuse C, and let's just sort of see what we can do with it. So because we didn't have anything special for this right triangle, this logic works for any right triangle. And because it works for any right triangle, it's got to be the case that a squared plus b squared equals c squared for every single right triangle that's out there. And that's it. We've managed to prove the Pythagorean theorem. Pretty neat. All right, that wraps things up. Thanks for watching, and don't forget to check out the other videos at chipmunkmath.com on this topic. I especially recommend, if you were watching the Advanced Understanding, you might like to check out the Pythagorean triples video. It's kind of interesting, and it's also really useful if you're going to be taking any standardized tests, and it's useful on tests in general, but especially if you're taking standardized tests, it can give you a little bit of an edge. All right, see you next time.